I'll be second. Take somebody upstairs. Good afternoon, everyone. Welcome. Thank you for coming. Trevor Asaph, board gaming and data mining. All the other stuff.
So, unfortunately, I only have 20 minutes to get through 4 months of material. Naturally, I have to cut some things, and naturally, I will have to go fast. This presentation will not explore the field of artificial intelligence as a whole. Rather, it will cover the key concepts relevant to the intelligence model encoded in my program. We will begin with AI vocabulary. Next, we will look at some algorithms. And finally, we will conclude by discussing my program, Watson. No relation to the IBM star. So first, we have the agent. The agent is the most basic component of our model. It is the entity whose intelligence is in question. Something needs to be intelligent, and we call that something the agent. An agent can be as simple as a doorbell, can be as complex as a girlfriend. The entity with which the agent interacts is defined as the agent's environment. Let's say that Pooh Bear is our agent. Well, then the 100-acre wood will be his environment. Interestingly enough, all the components of the environment are agents as well. Tigger's an agent. Christopher Robin's an agent. The heffalumps are agents. The 100-acre wood itself is an agent. But from Pooh's perspective, it's his environment. Simply put, an environment is a community of agents. For the mathematically inclined, you can think of the environment as the set, which contains the agents that the target agent interacts with. Now, such interaction is conducted through 2 types of instruments. Agents receive input data through a mechanism called a sensor. For example, Pooh can see, smell, taste, touch, and hear his honeypots. There are mechanical sensors as well. A doorbell senses a press. Agents care about this input information because they use it to choose their next action. Actions are performed by a mechanism called actuators. Pooh acts by unscrewing the lid. Doorbells act by projecting sound. And as you can see, a relationship develops between the agent and its environment, where they use these mechanisms to continuously upload and download information from each other. This model is significant because it gives us a basic idea of what it means to be intelligent. Agents receive information from their environments to then send new data back. Likewise, environments receive data from their agents to then send new information back. This cycle repeats, giving us our model. Now, the doorbell is one of the simplest examples of an agent. It is what's known as a table-based agent. These agents have specific sensor inputs mapped to specific action outputs. What makes a table-based agent so simple is the fact that very little processing is done to the input data. In fact, all a table agent does is traverse a virtual table until it finds a key that matches the input data. Once it finds this key, it then acts by outputting the corresponding data. A doorbell projects sound because a doorbell rings because the production of sound is mapped to the press of a button. Now, this next agent complicates things by introducing the notion of a goal. A goal is defined as the input that the agent identifies as urgent. A goal-based agent's intelligence model is quite different than that of a table-based. It doesn't use a table. Rather, it uses a set of hypotheticals, or what-if statements to choose its next action. This agent cycles through its possible actions and pretends to perform each one. If the result is a goal, then the agent performs that action. If not, then the agent what-ifs on the next possible action. If none of the available actions generate goals, then the agent chooses randomly. Now, the next agent takes things up a notch by introducing the concept of utility. This agent's model is similar to that of the goal-based model. A utility agent has a goal, but the way that it pursues that goal is more complex than its cousin. Whereas the goal agent chooses randomly between non-goal actions, this agent assigns numerical values, or utilities, to quantify the desirability of those actions. Whereas the goal agent discerns yes from no, right from wrong. The utility agent discerns better from worse. The best action, the one with the greatest utility, will be chosen as this agent's next action. Now, in order to generate such a utility, the agent applies what is known as a heuristic. And a heuristic is a function that analyzes hypothetical scenarios and determines how favorable they are to the agent. Now, I want to pause for a second and explore one of the most famous utility agents of the 20th century. In 1997, IBM's Deep Blue became the first chess program to vanquish the reigning world champion. Now, it seems so foreign. How can a computer play chess? How does an inanimate something like Deep Blue turn an input into an output? Let's take a look. First, Deep Blue plants a search tree. We will cover these in detail later, but for now, think of a search tree as an extended what-if statement, a way for Deep Blue to peer into the future of its environment. The basic idea is that if I play here, then my opponent has these options, and if my opponent plays there, then I have these options. Simple. Deep Blue then explores the fringes of this tree and applies its heuristic to the leaves for the last moves considered. Finally, Deep Blue sorts through the leaves and plays towards the one with the greatest utility. Now, Deep Blue is interesting because he has a sense of the future. By exploring his search tree, he realizes the later risks and rewards of playing in the now. But he has no sense of the past. All he knows is what could be, not what has been. Now, Deep Blue is successful because he can evaluate over 200 million moves per second. His search tree is enormous. Nevertheless, he is limited to a static, one-dimensional view of his environment. Given the same input, Deep Blue always responds with the same output, the same move every time. This last type of agent is much more powerful because it uses its past to reason about its future. This agent is the learning agent. The learning agent is special because it continuously modifies its heuristic based on the input that it receives. The learning agent is special because it continuously modifies its heuristic based on the input that it receives. In other words, its perception of the world, its sense of right and wrong, better and worse, changes in rhythm with its experience. On board Discovery, Hal sensed Frank Poole's ineptitude, and he used those observations to design his checkmate. Every time Frank made a play, Hal would use that input to modify his heuristic, and the more Frank played, the more Hal learned what kinds of moves Frank liked and didn't like. And the better he could predict Frank's next move. Now, to review, learning agents are utility agents that use their sensory information to modify their heuristics, to modify their perception of the world. Now, learning has a very specific purpose. It is to acquire information that one did not already have before. Obviously, this implies that the agent who learned was missing information to begin with, suggesting that the parts of the environment were previously unknown to the agent. Such ignorant agents inhabit what are known as discrete environments. Conversely, explicit environments are environments that contain omniscient agents, or agents that have complete awareness of their surroundings. Hal inhabits a discrete environment because he does not know where Frank is going to play next. But Hal tries to make his environment more explicit by learning why Frank plays where he plays, giving Hal a better sense of the future. Now, with these new concepts, we can now begin to understand the various levels of intelligence. At the most basic level, we have the doorbells of the world. Those static action-reaction mechanisms that seem to do their job for no particular purpose. On the next level, we find two-dimensional systems that differentiate between goal and non-goal states. The microwaves that cook and continue to cook until time is up. On the third level, we encounter more multi-dimensional entities with clever functions for choosing the next best action. Deep Blue is such an entity. And on the top, this is the class of agents who use their sense of what has been and what will be to checkmate their opponents. It was this elite class that inspired my program. Now, when I made that decision to make a learning agent for my senior project, I felt like hot stuff. Slight problem. How do you do it? How do you make a dynamic heuristic? How do you make a learning agent? I had no idea. I was missing the critical link that tied experience to decision. And all of a sudden, I didn't feel so hot. I mean, utility programs are still interesting. They only rule the world at chess and other cool games. But it didn't feel as rich. It didn't seem like I would be doing anything new. I looked at it anyway. Now, the first algorithm I looked into was called BFS. This stands for breadth first search. BFS allows its agent to peer into the future of its environment and sense the possibilities that lie ahead. BFS makes a search tree, similar to the one that Deep Blue used. In order to explore this future, we have to begin somewhere. This starting point is defined as the root node. To make a search tree, we begin with a node. A node describes a hypothetical action in the agent's future. This is the root node. First we expand the root by performing a hypothetical, another what-if statement. We pretend to place the root in our board, and we then calculate the opponent's next possible actions. Next, we cycle through each one of the leaves and perform the same operation. We what-if on our opponent's moves, giving us our possible moves. This process continues until we reach the desired depth, which in this case is 4. And just like Deep Blue, we apply our heuristic function to the leaves and we save our utilities in the nodes. Great. Well, there's something missing. Evaluating its leaves, the agent knows where it wants to be in the future, the greatest utility, but how does it get there? What does it do now? To choose the best immediate move, we apply John von Neumann's minimum-maximum algorithm, or minimax. Now, minimax has a precondition. It is only applicable in zero-sum games, games where my win is my opponent's loss, and vice versa. Not in terms of the final score of the game, the final result, but in terms of intermediate strategic steps. Because of this condition, minimax reasons that the maximization of my score results in a minimization of my opponent's, and vice versa. The fundamental idea is that you can predict your opponent's mind by taking the negative of yours. So if I want to predict where my opponent is going to move, then according to minimax, I reason that he will make the move with the least utility. The move that harms me the most. Conversely, when making my move, I try to maximize the utility, resulting in the move that benefits me the most. Now, we traverse this tree from its leaves to its root, maximizing on our pieces and minimizing on our opponents until we reach the top. On the 4th level, we minimize, because our opponent is choosing his next move, and we know that he will move where it hurts us the most. So, -1, -1, -2, and -4. Now, on the 3rd level, we maximize, because the move with the highest utility represents the best of our choices. The cycle continues, and the values propagate upwards until we reach 1 and -2. The values continue to propagate until we reach the root. Now, this root isn't very good. It's -2. That's not very good. But what if we were forced to play there? Then, according to minimax, our opponent should respond with -2. But what if he doesn't? What if he plays -1? Now, if I was Deep Blue, I would think, that's interesting. He should have played here. He should have played there. That's what I would have done. What was he thinking? And that, right there, was my reason. Right there, I realized that minimax is flawed. Now, minimax stipulates that the game must be zero-sum, and that makes perfect sense. But whose utilities are we comparing? Ours. How much we care about it, how much we don't. It's all from our perspective. It's using our heuristic. How can we compare our opponent's moves using our heuristic? We can't. If we want to predict our opponent's play, then we would have to use his heuristic. We would have to know how he interprets the board. And that is what my program is all about. Watson is more than a board gamer. Watson is a data miner. An intelligent agent that observes, gathering careful intel on his opponent and incorporating it into his war machine. Know your enemy better than he knows himself, and that is where Watson excels. Let's continue. All right, just a brief introduction. Watson is the AI engine behind my fellow program. This program was the focus of my senior project. So we began our analysis with Watson's heuristic. Watson's heuristic is unique because it consists of 2 distinct phases. It does not immediately calculate the desirability of the move. Rather, it begins by making specific, objective observations of the board. These are very simple observations. For instance, how many of my pieces are on the board? How many of my opponent's pieces are on the board? What is my mobility? What is my opponent's mobility? How large is my frontier? How large is my opponent's frontier? Etc. The main idea behind phase 1 is that you list and measure all the salient components of the environment. These components are Watson's tactical fields. Phase 1 ends when Watson finishes evaluating the tactical fields. Now, phase 2 was inspired by the timeless equation, subjectivity equals objectivity times how much I care. How much Watson cares is defined in his profile. Now, our profile is a list of numbers that contains exactly as many elements as there are tactical fields. Watson's profile is called TAsenProj. Each number in TAsenProj represents how much Watson cares about the corresponding tactical field. For instance, if Watson weights his piece count at 1 and his opponent's piece count at -1, then Watson cares about increasing his piece count exactly as much as he cares about decreasing his opponent's. Similarly, if Watson ranks his mobility at 6 and his frontier at 4, then Watson cares more about his mobility than his frontier by a factor of 3/2. TAsenProj's companion profile is OPROF. Now, OPROF is interesting because it's not a measure of how much Watson thinks the opponent should care about the move. Rather, it is a measure of how much Watson thinks the opponent actually cares. Okay. In other words, OPROF represents how much Watson thinks the opponent cares about certain aspects of the game. Now, such profile differentiation is significant because it allows Watson to interpret one board in 2 ways. The first way represents Watson's assessment of the board from his own point of view. The second way represents Watson's assessment of the board through his impression of the opponent's point of view. Phase 2 ends when Watson finishes calculating the subjective rank. Oops, I missed. Okay. Watson calculates this rank by multiplying the tactical fields, objectivity, by the corresponding weights, how much I care, as defined in one of the profiles. By the end of the heuristic, each leaf will contain a reference to both Watson's and the opponent's subjective rank. If the profile being used is TAsenProj, then the result is called an alpha rank. Conversely, if the profile being used is OPROF, then the result is called beta rank. Now, we find ourselves in a familiar situation. Our leaves have been evaluated. Our heuristic has been applied. We know where we want to move in the future, but how do we get there? What do we do now? Minimax is a bust. We can't use that. So we make our own. Again, they only gave me 20 minutes. I would love to walk through the algorithm that I wrote, M-star, but there's just not enough time. If you want to talk about it, you can go and find that. In brief, M-star is identical to Minimax, except where Minimax uses minimization to predict the opponent's next play, M-star uses beta ranks. Now, if I've done this right, there should be a glaring problem staring you guys in the face. Great. Watson can differentiate between perspectives, but how does he learn? Now, the secret lies in Watson's decision cycle. The cycle consists of 3 parts: observation, execution, and prediction. Now, we are very familiar with execution. Here, Watson plants his BFS search tree, applies his heuristic, and chooses his next move with M-star. Once Watson identifies his next move, the prediction phase begins. Watson performs one last hypothetical by placing his next move into an imaginary board and calculating his opponent's next moves. Watson applies his heuristic and assigns beta ranks to these next moves. Watson then selects the piece with the highest beta rank as his prediction, the move that he thinks his opponent will most likely play next. Finally, Watson places his next move into the real board and waits for his opponent to respond. After his opponent plays, the observation phase of Watson's next decision cycle begins. First, Watson identifies the last piece that his opponent played. Next, Watson compares its beta rank to the beta rank of his prediction. If Watson predicted correctly, then OPROF becomes more resistant to future modifications. If Watson predicted incorrectly, then he updates OPROF by averaging each weight with the value that it would have needed to be in order to synthesize the observed beta rank. With every play, Watson observes. With every play, Watson predicts his opponent's next move. With every play, Watson learns. Thank you for your time. time for questions, please. Yes.
So how good is it?
At Othello?
Yeah, can you beat it?
Yeah, you can. I kind of wrote it. No, but unfortunately, I spent the bulk of my time working on the learning part, which actually involved a tremendous amount of debugging. So I never, like literally, I started researching Othello strategy in like the last week and a half. So I haven't had enough time to actually identify the salient components of Othello. Like ideally, it's supposed to be hundreds of components long. This one has like 20. Yes, Sam.
So, I don't know, you might not know the answer to this, but the question about deep loop. Do you know, did it just do minimax, or
No,
did
it used
it
something-
assume imperfect plane, so try and...
It actually used a third cousin of Minimax. So Minimax has a close cousin called Negamax, and Negamax has a close cousin called Megascout. And I don't exactly know the difference, but I know that Deep Blue uses Megascout.
Alright.
So it actually, no, I do know the difference. It involves, you know what alpha beta pruning is?
No.
It's basically a way of reducing the size of the search tree by saying, okay, I've searched this far. I'm not going to search every move beyond this point. I'm going to evaluate what seems relevant at the moment, and then I'm going to only search specific paths. So it's kind of like how we do it.
Right.
This looks interesting. Let's research that.
Okay.
Yes.
Does Opro persist across games?
That's actually ideally it's not supposed to. Ideally, like, so in Othello, the game is, like professionals divide the game into the early game, mid game, and end game. So ideally you would have, wait, actually, sorry, I was getting ahead of myself. What was your question again?
No, continue. It's interesting. Continue your thoughts.
So ideally, Watson would have a sense, okay, so in the middle of the game, my opponent's most likely going to change his strategy. So it would refresh OPROV to the values that it thinks. Basically, it should refresh OPROV to the values that it's going to use for the middle game, and then as the game goes on, OPROV will take on a life of its own. And the same thing will happen with the end game, same thing will happen with the beginning game. The unfortunate part about Othello is that it's only like 60 moves long actually, because you start with 4, so it doesn't have that much time to actually take on the correct personality. Yes.
So if somebody beats Watson, will it copy the O-Prof into its W-Prof?
I actually haven't completed a game because so my search tree had been like 6 moves long, and so every time it goes, every time it plays, it takes it'll be there for a while. Because it's the branching factor of Othello is 7, so it's 7 and 6. It's a lot. Still thinking. It's thinking. Anybody else? Yes.
Is there any advantage to having a human mind in this like current world of advanced AI, or are we like looking forward to a war of the machines and Skynet taking over? And, like what differentiates the smartest human mind from the best AI mind?
So the greatest thing about the human mind is that if you think of the neural connections, we have an inordinate amount of neurons in our brain, and each neuron has like ostensibly an infinite number of connections to all the neurons around it. And this interconnectivity allows us to take ideas to identify like the thinking structure. And so, I mean, the next step is actually making an artificial neural network. And interestingly enough, in my research, there was a team that used a artificial neural network to actually generate a world-class, like the program went from, it was just a network, went from no knowledge of Othello to adapting and playing world-class levels. So it was cool, and it like learned the strategies by itself. So, yes?
If you played it against a really good person, would it try to copy that good person's moves? Or would it try to just use that to adapt itself?
No. The way I programmed it right now, DuckProf doesn't actually adapt to anything. It's constant, but its sense of what the opponent thinks is relevant, as defined in Prof, would adapt. And so, this one.
Are you going to continue working on this project?
Yes. This project is not over. The presentation is though.
Tell the audience how much you knew about programming and data mining, say 4 months ago.
Yeah.
I knew absolutely nothing about data mining 4 months ago, and I still don't really know. It just sounded like such a cool word. So that's why I had, it's actually not the correct usage because my dad told me it's not really what it is. But so I hadn't really known much about programming before this year, but I luckily enrolled in Mr. Considine's CS course, which is fantastic. I completely recommend it. You have like 5 hours free every night for homework. Anybody else? Yes.
What's the next step in AI? I mean, it's such a logic-driven thing, and it seems like it's used to human mind.
The whole field, or
Yeah,
Watson?
I guess the whole field, just from based on your research.
I would love to see it develop into understanding more of natural language. That seems to be like the next frontier that everybody's itching to get into. So that's what I think. There's actually a project called Alice that's doing something on that, and Mr. Snygers has a friend who's doing that. Anybody else?
Okay, that's it.
Great.